All right, hi everyone. Last time we were on 5.2 volumes. That's just the name of the section. And we finished off talking about what a cross section was. So remember, a cross section, very important to know what this means. This is the intersection of a plane with a surface. Okay, and by surface I just mean some object. And remember, what I meant by plane is, what is a plane? A plane is basically just a sheet of paper. So this is a plane here. Now you can orient it in a bunch of different ways. And so, for example, here's my eraser, like we were saying. If I take the plane and I pass it through like this, the plane, if it would stay still like this, if I pass it through the eraser, what I'm going to get is like this chunk right here, right? Whatever it passes through, I'm going to get the chunk and the inside of that. So the cross section there would be like a rectangle. It would be like this little rectangular piece here. So that would be a cross section. And then, but I can also, cut it like this as well. If I cut it like this, so it runs through it like this, then it looks like, I'm gonna slant it a little bit. Then it's a lot longer this way, right? If I cut it like this, it's going to be a lot longer on the side and shorter up top. So these are all just cross sections. This is what happens when I pass, a piece of paper or a plane through an object, and then wherever the plane and the object overlap as I pass it through it, that is the cross section. So depending on how the plane is oriented, like this, like that, you get different cross sections. But that's just the general definition of the cross section. And remember that this is the way that we define the volume of an object. The volume was this guy here, where this was the cross-sectional area. And as you might guess, that literally just means the cross-section, the area of the cross-section. So, like, if we think about it like this, I can hold this guy right here, right, the eraser, and then you can think of as putting it on a coordinate axis. So here is the starting point, let's call it just 0, and let's say, assume that this is like, I don't know, 6 inches long. So this goes to 6. So now we have units here. Okay, so in this case, this would be like 0 to 6. Still looks like a B. 0 to 6. And then what we're going to do is we need to figure out some cross sections. So let's say that we slice like this. If we slice like that, then at each point X, if I pick a random point X, I can make a slice, right? So at each of these points X, the area of the cross section that I get, so at any point X, what this looks like is kind of like this. The cross section kind of looks like that. So it's the area of the rectangle at a particular point X. That's what A of X is, and that's the cross sectional area. So the area of a cross section that you get at a point X. Now in this particular example, each cross section will have the same area, so this function won't depend on X. It'll just be a constant number. But in other cases, that'll change. And the next prop kind of shows that, like I was saying last time. If we have a sphere, notice that these balls have different radii, and those are representing the different radii of the circles that we get in our cross sections. So if I cut this guy like this, like sideways, then as you can see here at this very point tip here, you'll have the circle will just be a dot. And then as you get toward the middle, the equator, each circle, the cross section is going to be a larger and larger circle until you get to the equator, and then it starts decreasing again until you hit a point at the very other end. So the cross sections here of a sphere, at least when we're cutting it the way I showed you, are circles of varying radii. So let's calculate the volume of a sphere using this formula. Okay. So if we think about it, what I did is, again, if we put the sphere on the coordinate axis, this here would be some positive radius r, and then this would be the negative of that, right? Again, like this tip would be positive r, that would be negative r, or negative r, positive r. And then the point right in the center of this, which we can't see, and we're assuming that this is filled in, it's not hollow, so this is a filled in ball. The very center of this ball, that's this point right there. Okay, and then like we said, if we cut it like this, cut into the sphere like this, the cross sections that we get are like circles. We get different cross sections. So see, notice that this cross sectional, the area of this circle is smaller than the area of that circle when we cut into this. But let's just focus on one arbitrary circle, because that's what we're going to use to figure out what a of x is. So again, so we know that the integral goes from negative r to r at least. And this is going to be the volume of a sphere. This is one way to develop the volume of the sphere, which is really crazy that we're going to do this. Now, at the point x that we've picked, what is the area? So this is the point x that we picked. And from here to here, you know, what's the definition of the radius? It's the distance from the middle of the circle or the sphere to its boundary. So middle to the boundary, that's r. And notice that we can make a right triangle out of this. So you can make a nice right triangle out of this. And you know, this is going to be some ordered pair x, y, right? So this distance here is y. So you go x units to the right, y units up to get to this point, and then this is the radius. And so notice that y here is the radius of our circle in blue. Not the radius of the ball, but the radius of the circle in blue is y. So radius of cross section, what is that? We'll call it maybe small r, is equal to this distance y. But we can now express y in another way. Because of the Pythagorean theorem, we know that this relationship is true. We know that x squared plus y squared must be equal to r squared here. And then this means that y is the square root of r squared minus x squared, where r is the radius of the sphere. So this is the radius of the sphere. And you may say, okay, what about the plus or minus? Well, we're considering y as a distance, so we're taking the plus because it's like a distance. Okay, so this y, now notice that this is a function of x. This is why we did this, because we need a cross-sectional area as a function of x, the position x, where you're at on the horizontal axis. So the area of a circle is pi r squared, right? It's pi r squared. So this is going to be pi times then the area, which is the square root of r squared minus x squared. This circle, so the cross-sectional area is this. This is what the cross-sectional area is. So this is cross-sectional area. This is a of x. Because see, this function depends on x, which is really good. And let's fact check. If you let x be r, so you're at the periphery, you get r squared minus r squared, which is 0. So you get a circle of radius 0, which is good. That's what's happening. Our cross-section should go to 0. Because see, we just get a dot. And then also, if you put negative r, if you're at the other end, the circle also has radius 0. So very good. This is showing you that the radii change. The different values of x give you a different radii. Okay, so very good. So now this is pi times r squared minus x squared, because this was a of x, and then dx is what we had. That's the volume. Okay. And now to finish this, maybe let me just recopy it. So volume, so I have more space. This was pi times the square root of r squared. Okay, and then, so this is what we have. And then notice that this guy here is actually an even function. I messed one thing up. So remember, the formula for the area of a circle is pi r squared. It's the radius squared. I have not squared this. So the a of x is pi times the square root of r squared minus x squared, this whole thing squared, which is just pi times this. Okay, so I messed up a little bit. This square root doesn't belong there. Okay, sorry about that. So pi r squared, okay. Now notice that this is an even function right here, because the r is a constant. So if you think about a of x is pi times r squared minus x squared, what happens when you put negative x in here? This is pi times r squared minus negative x, this whole thing squared, but this is just the same as pi times the same thing. So, which is a of x. So a of x is an even function. Which is really nice, because then we can use this property that says that this integral will just be twice the integral from 0 to r of this guy. So it helps our calculations out a little bit. And then now this just ends up being 2 pi integral from 0 to r of r squared minus x squared dx, which we know how to deal with this. We just take each antiderivative separately. So this is now 2 pi times, the antiderivative of this is, because it's a constant, you just tack on an x, and because of the power rule, this is 1/3 x cubed, and we evaluate this from 0 to r. Okay, and then you can see if you stick 0 in here, that'll go to 0, that'll go to 0. So I don't really have to worry about sticking 0 in. So the meaningful part is just going to be 2 pi r squared times r minus 1/3 r cubed which gives 2 pi times r cubed minus 1/3 r cubed, which is, you know, if you have, this is like 1 minus 1/3 is 2/3, right? So this is 2 pi times 2/3 r cubed, which is the formula that we all know is 4/3 pi r cubed. This is the volume of a sphere. That's very amazing that you can do that. And it comes from, you know, the idea that we had that was very intuitive. You just add up the area of a bunch of, the volume, sorry, of a bunch of these small slices. And, you know, at first, if you use really big slices, it may overestimate or underestimate, but if you let your slices get really, really, really thin, then they become, you know, a perfect approximation. Okay, so that's really cool. Now let's do a few more examples where the shapes aren't necessarily so nice looking. They may look a little more strange. So now we're going to take a certain shape and then like rotate it, and then the resulting surface or object that we get, we're going to find the volume of that. So let me give you an example. So let's say you take find the volume of the solid So we're going to take y equals square root of x from these two numbers. So x is 0 to 1. And what we're going to do is we're going to rotate this little piece of the square root function, this little arc, around the x-axis. So we're going to rotate this around the x-axis to get like, you'll see it kind of looks like a bowl. So the square root of 0 is 0, so I have a dot here. Then if you stick 1, the square root of 1 is 1. So this goes to 1. And you know, square root kind of is like this little arc thing here. So we're going to take this guy, rotate it around the x-axis. So we get a symmetrical shape here down at -1, but you're rotating it into the board, so it rotates out of the board and then into the board until it hits this point again. So it comes like this, and then it goes into the board, which I can't do, and then comes back around and hits that. So when you do all of this, you get like some bowl-looking shape, which you need amazing drawing skills to do this, you know, very, very well. And I have like level 1 drawing skills, so hopefully this is like pretty sufficient on what it kind of looks like. It'll look like this bowl, right? A bowl that's tapering off to a point, kind of like a cone, but not exactly, like a fattened out cone. Okay, so this is the shape that we get, and so we want the volume of this bowl. So this is the same idea, is we are going to look at the cross-sectional areas. So we know that the volume is going to be given by this. So we're going from 0 to 1. And then if I pick a random point x, right, what does a cross-section look like? Looks something like this, like a circle basically, right? And this is just like the sphere. As you get close to this point, the circle will just become a dot, and as you get here, the circle will be this whole big thing here. So we can use this to determine our cross-sectional area. Now notice that the radius of this circle, this distance from here to here, is actually, from here to here, is just the square root of x, right, which is f of x. Because remember, what does a function tell you? It says at the input x, it tells you how high up to go. So at x, you go the square root of x up. So what we just noticed is that the radius of the cross section and you might have to, rewind this a couple of times, but the radius of our cross section, which is just this distance, or this one here, but let's just use that one, is the distance from the x-axis to the point on the curve, square root of x. It's on the arc, meaning that it's just whatever happens when you stick x into your function. So it's the output. Well, the output is the square root of x. So the radius of the cross section is root x. And so the cross-sectional area a of x, now it changes, right? Depending on what x is, you get a bigger or smaller radius, is going to be pi times the radius squared, which is just pi x. Okay, so that's our cross-sectional area. So this is technically a of x dx, and the a of x will get replaced with pi or pi x. Okay, does that make sense? And so this now just becomes pi x squared over 2, evaluated from 0 to 1. Again, the 0 doesn't do anything, so when the dust clears, this is pi over 2 times 1 squared, which is pi over 2. So the volume of this bowl is pi over 2. So you can fill pi over 2 liters or milliliters or gallons of water into it, depending on whatever unit you're using. Okay. So next up, you may ask, if you rotate about the x-axis, can you rotate it about the y-axis? And the answer is yes, definitely you can. So now we're going to rotate x cubed from x equals 0 and so find the volume of the solid table, and y equals 8 around now the y-axis. So let's think about what we're doing. Let's draw this out real quick. So we have x cubed, the cubic function. So x equals 0, we got, if you stick 0 into this here, it's 0. And then y equals 8. Notice that if you stick 2 in for x, y will be 8, right? Because you get 2 cubed. So that's how far along we're going on the x-axis. So we're at 1 here. And then at 2, we jump up to 8. So this is what our curve looks like. So x equals 0, remember, is this vertical line, is basically the y-axis. So this is x equals 0. And then y equals 8 is this horizontal line, 8 units up. So what we're taking is this little, I don't know what you can say, it's like a piece of a quesadilla or something, this little quesadilla piece. And we're going to rotate this around the y-axis. So now again, this is just going to look like a bowl. So in a symmetric fashion, this would be the curve, the boundary of this guy would flip and give you this. And then This guy, when you flip it around the x-axis, doesn't change, but this one will flip around to give you this. So then overall, we're finding this volume. We're trying to find the volume of this bowl here. We want this volume. Okay? And now notice that we have two options. We can integrate along the x-axis like this, so we can make circles as a cross section. We can get circles that look like this. Or what we could do, which may seem a little more natural, is to integrate upwards and look at cross sections that look like this instead. Like that. So now our discs, instead of being like this, they look like that. Which kind of makes sense, right? If we rotate about the y-axis, that's what the disc would look like. If we rotate around the x-axis, that's what it would look like. So we're going to look at this disc here. And now because of that, we're going to be integrating from along the y-axis. So now the area is going to be from C to D. Usually this means that these limits of integration correspond to a y-axis as opposed to A to B, which is x-axis. Now our area will be a function of y dy because we're going along the y-axis. Okay, so we know that C and D, C should be 0 and D should be 8. So we go from y is 0 to y equals 8. Now what is the cross-sectional area? Well, if we look here, this distance here would be the radius, right? Maybe I'll put it in a different color because now there's just so many colors. A lot of distractions. This distance is the radius. And at first it may seem like, how do you get that distance? Notice that we can rewrite y equals x cubed. We can interchange, this kind of means you can interchange between both, as the cube root of y equals x. So now this is like what we were talking about earlier is here now I give you a y coordinate and then you tell me the x coordinate, as opposed to the opposite. I give you an x coordinate and then you tell me a y coordinate. But this is perfect because notice that this distance is an x coordinate. It's a right or a left. It's an x coordinate. So here, look, I know the y coordinate at this exact point y. So I know the point y. This is just some arbitrary point y. I'd like to know how far to the right I am. This will tell you exactly that. So the cube root of this point y, whatever it is, it could be like 4 or 8 or whatever, tells you this distance x here. This here is x. And that's the cube root of y. So that is perfect. That's our radius. So the radius is the cube root of y. And that's very good because now we can figure out what the cross-sectional area is. So A of y is pi times the radius squared. So it's pi times the cube root of y squared, which is the same as pi times y to the 2/3. Remember a little bit of stuff from algebra is the cube root of y is the same as y to the 1/3. So if you square this, you're squaring that, and this is y to the 2/3. Okay. So let me erase a bunch of stuff so we can just do the calculation in peace now. So we're going to go, so the area of volume is the integral from 0 to 8 pi y to the 2/3. This is the area, cross-sectional area, dy. And then, again, this will be using the power rule. This is pi y to the, if you add 1, 2/3 plus 1, this is, 1 is like 3/3, right? So this will give you 5/3 here. And then remember that you're going to be dividing by essentially 5/3 as well. But when you do that, as you've seen a gazillion times, you just end up multiplying by the reciprocal of this. So this is going to be 3/5 pi y to the 5/3 evaluated from 0 to 8. Okay, and then when the dust clears, you get 96 pi over 5. So that would be the volume there of our other bowl. So now we're going to get into something slightly more complicated. Is what if our region isn't always, so nice? It has like a gap in it, and you'll see what I'm talking about. Like, so let's do this. Let's take volume of region obtained by, or let me say solid, sorry. Volume of solid obtained by rotating the region formed by y equals x and y equals x squared around the x-axis. Okay. Okay, so let's see where these two curves first intersect. So, if you take x, set that equal to x squared, that means that x squared minus x is 0. Pull out an x, and you get this, meaning that x equals 0 and 1 are the intersecting points, the x coordinates. And then if you want the y coordinate, you can just stick it into this, and you can see it's the same. So if you stick 0 in here, you get 0. Stick 1 in here, you get 1. So the ordered pairs of intersection are 0, 0, and 1, 1. So they intersect at these ordered pairs. So we see this. And then if you think about it, if you take like an intermediate point, like 1/2. So y would be 1/2 here if you just stick 1/2 in for x. But in this case, y would be 1/2 squared, which is 1/4. So this is bigger than that. So y equals x, the line, will be larger than x squared, at least in the interval that we're considering from 0 to 1. So they intersect at these points, and the line is on top of the curve. Okay, so the line is bigger than the parabola, at least on this interval. So this is the region that we're looking at, R. And now we're going to rotate this around the x-axis. So if you rotate this around the x-axis, again, you'll get something similar. This line here will rotate down, like it'll rotate down, and then this curve here, when you rotate it, it'll end up looking like this. So it kind of flips which one is on top of the other. So this will go down here, so this blade looking thing will flip down and look like an upside down looking blade, I guess you can say. Okay, and this kind of also makes sense, you know, like sorry, this should be attached here, so I don't know why I put it down there, but that's the only issue is this point stays the same and then the rest follows, so this goes there, so the parabola and then the line, there we go. Sorry about that. I was gonna say this looks a little wonky. Okay, so yeah, when you flip this around the okay, sorry about that. Phone technical issues. So what we're gonna have is, so this is the shape we get after we rotate, and like we were saying, you know, this thing comes outside and inside the page, or you know, the board or my wall, and so the volume that it sweeps out is the volume that this like little teardrop thing generates. And so it's actually just gonna be like, in terms of volume, will be this. It'll be this thing and this thing here. This is the volume that we want. So this inside isn't contributing to the volume. This is the tricky thing. So then when we make, you know, if I pick this point X and I make this little cross section, the problem is we only want to take into account these areas here and not anything in there. So how do we fix this? How do we deal with this? So we'll take the area of all of this, just find this big area, and then subtract off the area of this smaller thing. So maybe in a different color. So we'll take the area of the big guy, the green thing, and then we can also form, you know, the area made by this red thing and subtract off the red. So when you take the whole thing, subtract the red, you're just left with that. So how do we do this? So let's think about what we're doing. Let me redraw this. And so, let's see the best way to do this. Okay, redraw this. Then notice that the circle in red, the smaller circle, X here. This smaller circle here, what's its radius? Its radius is going to be from here to here, right? From this point to there. So the radius of the smaller circle, that's going to be basically how high up the parabola is, right? Because notice at this point X, we're on the parabola. Any circle I make is going to lie on the parabola. So the radius is just what happens when I stick x into the parabola, which is x squared. So the radius is x squared, right? If you stick x here and you go to the parabola, you go x squared units up on the y-axis. Now oppose this to, let me redraw that. suppose this to, if I take now the same point X, or roughly the same point, and I draw my bigger circle, now what is the radius of this guy? So if I draw this bigger circle, what's the radius of this? Now instead of going to the parabola, I go to the higher curve, which is x. So this is just going to be x. So if on the line, whatever you input, the output is the same. So the radius here is just x at an arbitrary point. So instead of having a disk as my cross section, you get what's called like a, not what is called a washer, like a washer from regular life. Washer is like this. The inside is missing here. So the cross section is actually a washer. Okay. And then what would the area of the washer be? Well, like we talked about, it's the area of the big circle, so this big area, this entire area here, minus the smaller area. If you take this red part out, then you're just getting all of that. And notice the radius here So then, notice that the small radius here, and maybe let me just put it in red, the small radius, like we talked about, or let me go up because we went up. So the radius here, which we'll call small r, because it's a smaller, it's inside, smaller radius, lowercase. Small r, like we talked about, is x squared. And then the larger radius, big R, is just x. So in our washer, this is what the bigger and smaller radii look like. So then, well, finally, after all of this, all the dust clears, what we find is the cross-sectional area, A of x. What we found is that A of x is equal to, so the area of the big circle is pi times x squared, so pi x squared, minus the area of the smaller circle, which is pi x squared quantity squared. Wait, I'll put a parentheses here. So that's the radius, that's the radius. So this is capital R, the big radius. This is lowercase r, the smaller radius. So the cross-sectional area is just pi x squared minus pi x to the fourth, which is just, if you factor the pi out, this. Okay, so then, because we were going along the x-axis, we were going left to right, right to left, whatever, the volume is the integral from, we started at 0, we ended at 1, of the area dx, so pi, and then, okay, and then again, this pi here you could just pull out in front, so this is the same as just pi x squared minus. So the volume is given by that. And now let's just do the quick calculation to see what the volume will be. or at least the calculus portion of it. So the volume is going to be pi times this guy and then, you know, if we do the antiderivative or the power rule for the integral, this is just pi times 1/3 x cubed minus 1/5 x to the 5th, evaluated from 0 to 1. Okay, and again, if you stick 0 into these guys, everything just disappears. So the only meaningful comes from sticking 1 in there, which will just be 1/3 1 cubed. And then this is just, and then if you get a common denominator of 15, this is 5/15, this is 3/15. So then you get a 2 up top, so we get 2 pi over 15 as the final answer. So yeah, it's kind of weird. So the inside doesn't contribute to the volume at all, so you need to reconcile that by not having like a disc as the cross section but a washer to exclude the inside. So just the outside part of the washer, just this outer part, is giving us an area slash volume when you thicken it, not the inside. Okay, very good. Let's see how we're doing on time. So then, let's do more complicated examples. So now, and as you notice, the best way to kind of tackle these is to just draw everything out and like reason it from scratch. There's like a set of formulas that you can like write down, but you really have to know geometrically what's going on to use the formulas anyways. And then you kind of know everything at that point. So it's better to just draw everything out. So okay, so in the book it says the region in example 4, which I didn't label the regions, but the region that it's talking about is the one from the last problem, basically. So the region from the last problem the one you got from y equals x and y equals x squared, about the line So now we're flipping this thing not around the x-axis or the y-axis, but another line. The line 2 units up. So a horizontal line at 2 units up. That's what this thing is. So let's again draw this out. So we saw that they intersect at 0, 0 and at 1, 1. I'm going to put this kind of low just to have some space. And remember, the line was on top of the parabola. And so if we're flipping this about the line y equals 2, the horizontal line y equals 2, we're getting something similar as, last time, normally the y-axis is just y equals 0, the x-axis is x equals, the y-axis is x equals 0. So we've done this before, it's just now it's not as like, common, I guess, but the same idea applies here. So when you flip this thing around, this point 1 will go to 3, and then 0 will go to 2, so this will go here, and then this guy was on the bottom, right? Now the parabola was on bottom, this will be on top. So the parabola will be on top. So this will go to 4, sorry, not 3. So this will be on top. And then the line will be on bottom. Okay. So this point goes to 3, that point goes to 4. And then we flipped kind of what happened. So the parabola is on top and the line is on bottom. Okay. So now again, to draw this stuff, you need really good drawing skills, but at least we can kind of draw what the periphery here looks like outside. So this is going to look like a bowl that's tapering off, maybe kind of like a conga drum or something like that, in a sense, with like a really flat bottom. So this is what we have. And again, the inside here, this doesn't contribute to the volume. It's only like this outer part that's contributing to the volume. So this is what makes this tricky. But the same principle that we used, we can apply again by using the washer. So if we use the washer, we can kind of do the same idea. So with the washer, what do? We subtracted the smaller area from the bigger one. So and you may be wondering, like, how did I get this as 4? Well, notice that this is like 2 units away from the line. So symmetrically, this point has to be 2 units away as well. And how this point was 1 unit away from the line. So this point also has to be 1 unit away at 3. Because this point goes here and that point goes there. Okay, so if we make a little circle here, let's make the smaller circle first. So that's a small circle, and again, this is just at the point X. What is this radius here? Key is to figure out what this radius is. So small r. Okay. So now we're not measuring from the x-axis up to our point. We're measuring from 2 to the point. So what we could do is say it's this big distance here, which notice from here to here, we could do this, or we're saying it's the distance from 2 to this point. So it's going to be 2 minus this guy here, the function, which is the line. And then maybe it would be easier to actually do this, as if we look at this radius here to see that this radius is the same as that one. Okay, so maybe let's look here so it's less complicated. So this is the line here, right? And so this is the radius. So then small r. Okay, so from here to the line is 2, right? From here to the line is 2. And then from here to here, because this is the line, we know that this point here corresponds to x. Because on this line, y equals x, whatever you stick into the function, you also get out. So this is x units up, and then this is 2 units up. So you take the large distance 2, and you subtract x from it. So this is 2 minus x. Maybe let me write that here bigger. So the small radius is 2 minus x. And then now, let's look at the larger radius. Now if you look at, just with the change of the color. Now if you look at the bigger radius, now this is what we're looking at. So instead of being on the line, we're on the parabola. So this point here, if I stick x into the parabola, how high do I go? I go x squared units up. So this, from the x-axis to here, the small distance is x squared, and then the large distance is 2. So this piece is 2 minus x squared. So capital R is 2 minus x squared. So the entire distance minus this small sliver here, so you get that. That's the distance from the parabola to the line. So big distance minus that small one gives us what we want. Okay, and then now it's the same idea. We know the smaller and the larger radii, so the volume, or the cross-sectional area, that's going to be given by the bigger area, so pi times 2 minus x squared, so this is the radius, pi r squared, minus pi times the smaller radius, 2 minus x squared. Okay, which is very nice, because now we know that the volume is going to be, again, remember we go from 0 to 1 on the x-axis, and then this is the cross-sectional area, which again we could factor the pi out, or maybe let's not for a second. Yeah, if we factor the pi out, it'll just go in front of the integral. So this is 2 minus x squared. Okay. Now if you're wondering how to do this, you would have to like FOIL each of these out, expand these out. So for example, like 2 minus x squared is like 2 minus x squared times 2 minus x squared, and then you FOIL this out to get 4 minus 2x squared minus 2x squared plus x to the 4th. And then this would combine into 4 minus 4x squared plus x to the 4th. So you would expand the other one out too, and then basically just combine what you have and apply the power rule. So I don't think that this would be the best use of our time to just go through this. If you guys have questions, definitely ask me, but after doing all of the algebra and whatnot, this will give you the answer of 8 pi over 15. Okay, so the idea is that we really have to be able to draw what's going on. Okay, sweet. So 8 pi over 15 is our answer. And then maybe we have time for one more quick example. Is now, let's take So we're doing the same functions. So we're doing y equals x and y equals x squared. That region created by these two around now the line, this line, x equals -1. So this vertical line at -1 units up. Okay, so we drew this 1,000 times now. So the line is on top of the parabola. That looks kind of nice. I wish I could do that every time. And then this is at 1, and that's at 1. And then -1 is where we have our line. X equals -1 is this vertical line, -1 units to the left. So now notice that this point, again, is 1 away from here. So when we flip it around this line, this thing flips like that. The leaf flips like this. So the origin, which is 1 away, needs to be 1 away, so it's at -2. And now this guy, which I should probably need more space, so let's call this -2, call this -3. And this guy is 2 units away, right? Because it's at 1 to the right, so it's 1, 2 units away. So it has to be 2 units away from this, so here. Same height though. So same height, but different x coordinate. So you flip this around this guy. So then yeah, this point went here, this point goes there, and then here the line will stay on top of the parabola because you're flipping it like this. Maybe I can, this is not very curved. Let me see if I can get something curvy, something that'll bend a little bit. Okay. So this is a very horrible attempt, but see, this is kind of what we have going on. So if you flip this around the x-axis, you'll get the same thing. So the curvy thing will stay on the bottom of the line. Okay, sweet. Sorry, did I say the x-axis? I meant the line x equals -1. Okay. So this is what we have. And then, so we need the volume of this like more strange bowl looking thing. But again, remember the inside here does not count. Only the peripheries are generating the volume here. And so we kind of need to do the similar case as with where we stacked the discs this way. As opposed to going up and down, we need our disc to look like this. So we'll have one disc. We'll get a washer again, except our washer will look like this as opposed to this. So our washer will be sideways. So now the inner washer, so if I draw, so let's take some arbitrary point y. This will be what the inner circle looks like. Now, the goal is to figure out this distance here, right? From the center to the edge here. Let me just call this point y. So that point right there is y. Okay? Now notice that it's 1. If you go from here to here, that's 1 unit. So the small radius is 1 plus. And I'll talk about a more suggestive way of writing this in a second. It's going to be 1 plus, so this distance plus. Now, if we think about, again, the line, if we think about f of x equals x, that's the line. You can also think about this, like we were saying, I give you an x coordinate, you tell me the y, but you can also think about it as I give you the y coordinate, you tell me the x. So you can think about this as f of y equals x equals y. This is not too revolutionary because nothing changes here. But now the paradigm is you hand me the y coordinate and then I tell you how far to the right to go. So if you give me this y coordinate, you tell me to go the same unit. So if y is 1/2, x would be 1/2. If y is 1/3, x would be 1/3. That's what this rule tells you. But what this means is that this distance here is x. So we're going 1 plus x. That's the big distance here. Which more suggestively is x minus -1, which is -1 is the thing that shows up here. And notice last time what we had was like, we had our function -2, or we had 2 minus our thing, and so you can kind of maybe see a little rule that's coming, a way of doing this in general. So the small radius is this, and now we want the bigger radius. Then the big radius here is again is if I tell you this disk was made at y units up, is what is this distance again from here to here is 1. So capital R is 1 plus. Now what is this distance from here to here? Now we're on the parabola. Notice that if g of x, which is y equals x squared, if you take the square root of both sides, x equals root y is another way of writing the parabola. So now if I give you the y coordinate, its square root will tell you how far to the right or to the left to go in a sense. So we know that if this is the point y, then now this is x which is root y. Whatever y is, you take its square root and that tells you how far to the right to go. So this is 1 plus root y. And here, there's a small mishap. See, this is a function of y. This x, because x equals y on this line, we want to replace this with a y. So we're going to replace that with a y. So let's change this to a y. This is like that. Sweet. So now that we know what the radii are, the bigger and smaller radii, it's the same idea. So now our washer, like I was saying, is horizontal. See, the washer looks like this. So we only want to count this area in red. Okay, so how do we do that? Same way we've been doing it. So remember, originally the two functions intersected at these points, right? So we're integrating down to top along the y-axis, but that's still 0 to 1. So the volume is going to be 0 to 1. Now we need a cross-sectional area as a function of y. Well, we know what it is. It's going to be pi times the bigger radius squared minus pi times the smaller radius squared. And then this is now a dy instead of a dx, because we're going along the y-axis as opposed to the x-axis. And then again, if you want to figure out how to do this, you like expand this out by foiling it and everything, but the final answer just ends up being pi over 2. And if you guys have questions about this, definitely just please ask me in class. Okay, so definitely think we hit our time limit. Awesome, thank you guys so much, and I'll see you next time.